Okay, we have here today another interesting integral from the UNSW CPMS Integration B 2023. This was semifinal round 1, problem 1. We have the integral from 2 to infinity, natural log of 1 minus 1 over the floor of x squared dx. Okay, now to get started with this, the first thing we really need to deal with is just having the floor in an integral. Now we've done a bunch of these in the past, and usually what I do is one of two things. I either will use a graph to get a feel for the floor function, or we can break up our bounds where the lower bound and the upper bound only differ by 1 and they're integers. And then what happens is the floor just gets reduced to a constant value. So let's try this and see how it works. We'll just look at one of these. We can look at this integral just from 2 to 3 of this thing. And we'll have natural log 1 minus 1 over, and then we'll have the floor of x here squared. But now the floor will round us down to the next greatest integer. And because our bounds are 2 to 3, the floor is just going to round us down to 2. So this value is always going to be 2 on these bounds. But then we can just simplify this and rewrite. So this is going to become 1 minus 1 over 4 is going to be just 3/4. But now this is just a constant value. So we can actually bring it out front of the integral, and we integrate this, and we just have natural log 3 over 4. Integrating 1, we just get x, and we just need to evaluate this from 3 to 2. But doing that, we're going to have natural log 3 over 4. But then plugging in our bounds, we get 3 minus 2, but this is just 1. So this whole thing is going to just be natural log of 3 over 4. But now this answer just gets us from 2 to 3. We have to do the same thing from 3 to 4 and 4 to 5 all the way to infinity. So I think what I'll do instead is let's just look at a general case of any one of these integrals separated by 1. So we'll integrate from a to b, where we know that b minus a is going to be 1. We're setting it up that way. And a and b are both going to be integers. And so then what's going to happen is we're integrating ln 1 minus 1 over the floor between a and b, but that's just going to round us down to our a value. So this here is going to become a squared. Then we can get a common denominator here, multiplying by a squared over a squared, so we can rewrite this again. And this is going to become natural log a squared minus 1 over a squared dx. But again, just like our integral from 2 to 3, this is just a constant value, so we can bring that out, and we're just integrating 1. So we're going to have ln a squared minus 1 over a squared. Integrating 1, we get x, just evaluated from b to a. But then this is going to just become ln a squared minus 1 over a squared. And then evaluating this, we're going to get b minus a, but we've already said that's just 1, so that part's going away. And so then we just have this for our general form for any one of these integrals from a to b. I'm just going to clean up the board to get some more space. Okay, so now that we have this general solution for any of these integrals where b and a are integers separated by 1, now what I want to do is write this as a sum, because we have to sum up all of these integrals starting where a is 2 and then a is 3 all the way to infinity. So I'll just write this as a sum, and what I'm going to do, instead of using a, I'm going to change the variable name for this lower bound, and we'll just call it n. It's supposed to be like to use n. So we'll start at n equals 2 because that's our lower bound here. So we're going from 2 to infinity. And then for each term, it's just going to be this thing. It's going to be natural log n squared minus 1 over n squared. But then just kind of expanding this out, we already found the first term when we did our integral from 2 to 3. So this first one is going to be natural log of 3 over 4. Then plugging in a 3, we get natural log 8 over 9. Then we'll have natural log 15 over 16. And this pattern is just going to keep going on and on forever. But then just noticing what happens when n is approaching infinity. Well, this thing right here becomes 1. So this thing at the end, when n goes to infinity, this is just going to be natural log of 1. Then by log properties, what I can do is I can rewrite this, but I can rewrite it as multiplication. So I can write this as natural log of 3/4 times 8 over 9 times 15 over 16 times 24 over 25. And this is going to go on and on like this forever, but all the way until we get to 1 for that one. But then with this, I can actually rewrite it again kind of carefully. So what I'll do here, I'm going to actually write this as, I'll write my 3 as 1 times 3 over 2 squared. And then this one, 9, I can write as 3 squared, and I can write this as 2 times 4. And then this I can write as 3 times 5 over 4 squared. And this I can write as 4 times 6 over 5 squared. And this pattern will just keep going like this forever. But the reason I break it out this way is because we're going to get a whole bunch of cancellation. I could take 3 squared and cancel it with 2 3s here. The same thing with the 4s. The same thing with the 5s. The same thing with the 6. And the same thing all the way to infinity. So what's going to happen here is everything to the right is going to cancel out. We have a 1 here, but it's just multiplying by 1, so that's not going to change anything. I can take this 2 and cancel it with 1, 2 here. And so we're just left with this 1/2 here. So for my final solution, we just have natural log 1/2. So there you have an interesting problem from UNSW CPMS 2023. Thanks everyone for watching. Have a good day.